in-person speaker this week. And so for those of you who might be on campus and want to remember what it's like being in the same room as other people, we're over here in Mann Hall, and we definitely got plenty of room and invite you to join us. I do want to thank you all for being here, and I want to introduce our speaker for this week. Our seminar speaker for this week is a department alumni, Dr. Tracy Stover, who's currently a principal engineer for Savannah River Nuclear Solutions LLC and lead of the Criticality Safety Group for H Canyon, the nation's only remaining industrial scale radiochemical separations facility. He has also supported work for the deployment of the mobile plutonium facility, decommission of the Portsmouth enrichment plant, multiple surplus plutonium storage and disposition programs, and validation efforts on scale, MCMP, and the CFIS. Prior to Savannah River, Dr. Stover worked with Westinghouse Electrical Company and as a reactor core engineer and spent field pool engineer. Dr. Stover holds a BS in physics from Murray State University and both an MS and PhD from Nuclear Engineering Department at NC State University. He also holds professional engineering licenses in both North Carolina and South Carolina and is a member of several national committees through the American Nuclear Society. So obviously, thank you for being here. Welcome home.
Oh, thank you very much.
I'll hand the floor over to you.
All right. And I assume I'm going to be far enough away from people to get rid of this thing.
Yeah, you'll be
okay.
covered here.
All right, that works. So I can actually breathe while I'm talking. Okay. All right then. I will try to maintain somewhere where you can actually visually see me from the video feed, but mainly look at the presentation. So we're going to be talking today about some basic things like chemistry, gravity, and geometry, and how we integrate realism, real-life scenarios, real-world considerations into our criticality safety evaluations. And so just for a little bit of a background, I'll start with you. What is criticality safety? Why is this niche of nuclear engineering important? We'll talk about some of the common bounding assumptions that go into criticality safety and why, in some cases, those might not be the assumptions we want to make that are really reflective of reality. And I keep getting these admit invitation. Okay. Okay. And then once we go through this little bit of a background, I want to cover with you some specific examples in 3 of our facilities where we've been trying to bring real world considerations, real life, logical aspects of handling of nuclear materials into these analyses. And we got about 5 examples here, which means we're only going to spend a few minutes on each one, but that'll be enough to kind of touch on the idea, and so you can get an idea of why we are doing what we're doing. If you have some specific questions, of course, we can double back at the end and address those. I'll wrap this all up with you. What is the quote-unquote realistic criticality safety evaluation? So in K area, we look for the simple way to store plutonium, or how we have extended some linear hand calculation methods into nonlinear space. Looking at the mobile plutonium facility, how we use these simple control schemes for plutonium on the go, or rather enhancing the flexibility of that facility by applying some very basic plutonium chemistry and even some first principle physics. Finally, the main facility I've supported over the last few years is the H Canyon separations facility. We'll be talking about a variety of scenarios there, getting some new not credible scenarios, or how we couple dynamic chemical simulations to crit safety evaluations, dissolving better and dissolving faster, or how we've been able to enhance the disposition of certain nuclear fuels with chemistry and geometry. And finally, how we've been able to upgrade or downgrade some of our control mechanisms and equipment to enhance our mission development and our throughput. So what is criticality safety? Basically, a criticality accident is the inadvertent creation of an uncontrolled nuclear chain reaction that is without shielding or confinement. Or the better way to say it is you've accidentally made a nuclear reactor somewhere where you don't want it. They can initiate in the matter of a few milliseconds, and they can last anywhere from a fraction of a second to several days, depending upon the geometry and the type of materials involved. Releases large amounts of energy in the form of heat and radiation that can be easily very lethal, especially if you have physical operators present doing hands-on activity. The radiation doses to personnel are in the hundreds to thousands of rem in a matter of seconds. So it's a very serious accident to happen. 22 have been known to happen, are known to have happened on hands-on processing facilities around the world, costing 9 lives. 38 additional ones have been known to have occurred in laboratory settings. Those cost 12 lives. We usually focus on the process ones because those are the ones where physical people are handling physical materials. The laboratory ones, most of the things that have happened in laboratories are heavily shielded and away from personnel. The ones that did result in injuries and fatalities, those were typically very early on, or those were cases where personnel unfortunately chose to violate some of the laboratory procedures to try and do an experiment. If you don't have a severe injury or a fatality, there are still other consequences to a criticality. You can have non-lethal injuries, non-lethal radiation exposure, still pretty bad. Damage or loss of equipment and special materials, regulatory scrutiny and fines. At best, you're going to have schedule setbacks and replacement costs of the materials. So the job of the criticality safety engineer is really to prevent an inadvertent criticality. And we do this essentially by managing the neutron multiplication of our system for all normal and credible abnormal conditions. And I really want to stress that word, credible. Because that's what we're going to be focusing on when we talk about realism. What is actually a credible scenario that happens? Of course, you include biases and uncertainties, extra administrative margin, and in general, the criticality safety engineer will work to what we call the double contingency principle, and I'm quoting this straight out of ANS 8 series standards. It is process design should incorporate sufficient factors of safety to require at least 2 unlikely, independent, and concurrent changes in process before a criticality accident is possible. And the reason I quote that, I don't directly quote things very often, is that several generations of people have went into ensuring that that is the appropriate principle to follow for criticality safety. So if you take a look at this timeline down here, it goes from about 1943 up until the year 2000. You can see the majority of the criticality accidents that have occurred in the United States and in Russia, mainly during the late 50s and early 60s. That was a time when both of those nations were really ramping up the production of fissile materials for the Cold War. And there wasn't really this structure in place, there wasn't the knowledge base in place to prevent criticalities. Around about 65, 66, the very first criticality safety standards began to be introduced, and the accident rate more or less dropped off. You see a couple more occurred early 70s, late 70s. The last one that we know about and has been documented and detailed occurred in 2000 in Japan. So very serious, but fortunately, it's been quite a while since we've had a criticality accident. There's some speculation that something may have happened in Russia a couple years ago, but there's been no official documentation released upon that yet. I already mentioned the ANS 8 series standards. Just like a number of different industries, nuclear has standards that are worked to. ASME has standards, IEEE has standards. ANS publishes the Series 8 standards on crit safety. 8.1 is kind of the father standard for handling nuclear materials outside of reactors. Some other ones that you may come across, 8.7 is for storage of fissile materials. 8.15 is for special actinides. That's the things that are other than uranium and plutonium. So stuff like your americiums, curiums, things like that. 8.17 for storage and handling of LWR fuel outside of reactors. We also have some Code of Federal Regulations for radiation exposure. DOE, I'm from the DOE side of the complex of the world. So we work to 10 CFR 830. NRC, commercial side, you'll be working to 10 CFR 2021. I tend to forget. I live in the DOE world far too much. And then our regulator, the DOE, also issues their own working standards for how we analyze our facilities, how we are to prepare a criticality safety evaluation, and what needs to go into that. So what are some of the basic things that we do to protect people when we are talking about criticality safety? Well, we control the things we can control. And in that case, we typically put our controls on what we call the magic Mirv. This is a mnemonic. It stands for mass, absorption, geometry, interaction, concentration, moderation, enrichment, reflection, and volume. Physical parameters that affect the multiplication of the system that we can control. Some ways that this has been done is single parameter control. We put multiple controls or restrictions on a single parameter, like you can only have so much mass and you have to verify that mass with independent samples. You have to have a safe geometry that you can't go critical in no matter what, things like that. Some of the things that we often assume in our evaluations, and it may not be realistic to do so, are optimal conditions of moderation, reflection, enrichment, and absorption. You're not always going to have the maximum enrichment possible. You're not always going to have the maximum reflection possible. You're not always going to have the minimum amount of neutron absorption. So we assume the maximums because they're easy to defend. You know, if you say you've modeled the extreme ends of the capability, well, there's not really a lot of question as to what's happening in other conditions because you've bounded it. It's an easy situation to defend, but you're touching on theoretical conditions. For example, maximum density. Anyone who's worked in nuclear fuels know that you have to put a lot of work into getting something to anywhere close to its maximum theoretical density. So let's just take this simple example. Say you wanted to take a couple things as heavy as a bowling ball and hover them in midair, perfectly positioned tangent to each other with an exact spacing in between them. Think that's easy to do? No. Consider this too. And this one you can even try at home if you want, kids. Take your garden hose out, pour a pile of sand in your driveway. Now take that garden hose and spray that sand into a perfectly homogenized sphere where every particle of sand and every molecule of water has an exact optimal spacing between it. If you can do that, good for you. You've scared me. But sometimes assuming these things like idealized spacing or optimal moderation just isn't realistic. Even so, assuming things magically form into a sphere when they're going to end up in a pile or a slab is overly conservative. So now that we know some of the things that we can control, some of the ways that maybe we put too much conservatism into the analysis, let's talk about bringing some reality back into it. The first example I'm going to give you is with the K area plutonium storage complex. This is a facility at the Savannah River site. Basically, this is where all of the DOE's excess plutonium is stored. Excess means it's not in any other programmatic function. It's essentially waiting disposition. So the old method for storing this material says you have an infinite sized array, and every package in that array has been arranged to where it's physically as close as possible. So if you're talking drums of material, that's triangular lattice. you've also, in these analyses, arranged the material to where they have been somehow moved inside their package to a closest packed cluster. Usually this meant hovering the plutonium in mid-air and bringing groups of 4 of them close together in the arrangement. Well, that kind of ignores gravity, and it also ignores the fact that we have a finite-sized room to put this in. Another assumption was you have an overmass, okay? You've misloaded the package, not by a few grams, this is plutonium, it's tracked to the gram, but by up to 100% overmass. Fire damage, you assume that the packaging material forms an optimally moderating mixture with the plutonium as it melts. Okay. Handling, well, we crushed multiple containers where they'd have the biggest impact at the center of the storage array. You can model just about anything, folks. Well, the results were we have very restrictive controls throughout the facility, and extreme emphasis placed on mass and conformation, very big emphasis placed on the NDA program, lower than desired storage capacity, and all of this to get you limits that were not much better than the single parameter values from ANS 87. How do we turn this around? Well, first, we limited the analysis to arrays as they were actually able to be produced. 3 to 4 tiers in a finite concrete room. We modeled the actual design of the packaging. We modeled the actual spacers that they're required to be upon, so they're not closest packed arrays. These are in 4 packs, and you can actually see one of our service technicians there taking some neutron dosimetry readings from the materials. We contacted our fire protection folks. We talked to them about what could actually happen, and we talked to our operators about how they could actually damage one of these packages. And basically what we come up with is, if it's going to happen, you can fire damage one of these packages. You can crush one of them on a pallet. That's about the worst that you can do in all realistic senses. We had a very detailed analysis of the people who can ship plutonium to us, for example, the other national labs. And because of how well the accountability programs are set up, anything greater than a 10% error in mass is just not credible. The result is very simple controls on packaging and handling, and we credit those programs like accountability and fire protection. But we took it a step further. We said, okay, this is all great, but we're still running lots of code. This is just a hunk of plutonium inside a steel drum. They were able to store stuff like this 20 years, 30 years before they were using computer analysis. Why are we wasting months doing analyses? Well, we went back and looked at what we call the linear surface, limiting surface density method. I was originally developed some of these idealized concepts of bare metal spheres, optimally spaced in a cubic array. Said, okay, we're going to take our real package, which has a lot of interstitial stuff that blocks the neutrons from talking to each other, and we're going to model that. And well, lo and behold, it's not a linear behavior, but it is a very easily characterized exponential behavior. So what we did was we said, okay, we can get these coefficients for this package design for this type of material, and we can go back and revise this simple linear method, and we can compare things like the number of packages in the array, which is this capital N value. We can compare that to the spacing between those packages, which is this A sub N value. And we can design our array such that any package that fits this mass envelope with this type of material is perfectly safe to stick in there. We can also do very simple perturbations with this equation and be able to scope out, without doing a lot of computer analysis, would this new type of material and package have some kind of effect on our array. Don't get too impressed by the math there, because what it really boils down to is a rather convoluted comparison of geometric and material buckling. You even see the extrapolation distance in there, your lambda of your array. So this is really just a buckling comparison for an array. It takes some effort to derive the constants, but once you have them, you don't really have to do a lot of more computer analysis for minor perturbations to your storage facility. Moving on, let's talk about the mobile plutonium facility. It's seen here with its sister facility, the mobile uranium facility. MPF is the one in the kind of light gray tan there. Savannah River National Lab maintains MPF. Oak Ridge National Lab maintains MUF. These are deployable capabilities. And the picture you see here is from a training mission that's in Alaska, actually. So when the facility was originally designed, it was laid out in mass control zones, which is a very typical crit safety approach. But it was limited to storage of 5 kilogram plutonium-239 metal hemishells only. This, however, required a lot of confirmations on size, shape, and mass prior to receiving the material. Okay, this works really great if all you want to do is disassemble weapons. Okay? But if you want to do anything else with this plutonium facility, you're kind of stuck. It also relied very heavily on an NDA program. And this receipt process then became your bottleneck. And bottlenecks, particularly in, say, a battlefield scenario, are not things you want to have. So it also includes container-based mass zones, item limits versus mass limits, assumed only one container type, but it did not credit that one container type, and it made no allowance for samples. And surprisingly, a lot of work went into developing this. The original analysts ran over 4,000 MCMP jobs and essentially came out with the same limits that you get from ANS 8.1 or ANS 8.7. Well, what did we do to kind of bring some realism into this? The first objective was to simplify the control scheme. We analyzed 2 bounding types of containers made out of aluminum and stainless steel that are very commonly used. We analyzed a bounding type of instrumentation. Of all the analytical instruments that are in the facility, their neutron multiplication impacts are bounded by one that kind of encloses the material in a polyethylene annulus. So that's the one we modeled our upsets in. We looked at upsets in handling and processing, inadvertent interaction, inadvertent moderation, inadvertent reflection. We got rid of some not credible events due to the nature of the process. Beryllium reflection was not considered not credible. You're not going to melt this material while you're handling it. That was considered a not credible now. You're not going to have inadvertent introduction of moderation into the glove boxes. They're just in dry facilities. There's no water or other hydrogenous materials to introduce. There's not going to be any errors in final packaging because we have a very stringent NDA program on what's coming out the back end of this facility. Finally, natural phenomenon. This is a mobile facility. It's meant to be deployed anywhere on Earth. So you can't really analyze natural phenomenon hazards like tornadoes, hurricanes, snowstorms a priori. But the mission of the facility is expected to only be a few weeks or a few months. So statistically, it's unlikely that you're going to be stuck in that scenario. What it boiled down to is we were able to set a universal 6.5 kg mass limit for each of our control zones, and that is regardless of shape. It's considerably higher than what they had before, and it's a simpler control scheme. But that wasn't all. We said, okay, we've got that. Let's expand the flexibility. We analyzed the typical can bag can configuration. We analyzed temporary storage of flooded containers, inadvertent placing of containers into flooded containers into our instruments. We gave them the ability to use these radiation shields inside their glove boxes. We gave them the ability to use the radiation shields inside the storage array for when they receive materials. We said that, okay, the materials can be subdivided into multiple little chunks, and those are bounded by a more restrictive geometry of this cylinder. We made allowance for plutonium-bearing solutions by restraining them to standard single parameter mass limits. We looked at the chemistry of different forms of plutonium: oxide, oxalate, fluoride. We pulled up a handbook values for plutonium metals and said, okay, if we compare the densities of the plutonium in the metallic form to the density of the plutonium in these other chemical forms, well, for any of the credible things that we could actually receive, they fall below the criticality safety line. So if you're good for metal, you're good for oxide, you're good for oxalate, you're good for fluoride. And finally, those containers, well, it turns out the aluminum and the stainless steel ones that we modeled actually bound other types of container materials. So we looked at basically the scattering physics that go into things like tin, brass, copper, a variety of other metals that you might typically encounter packaging fissile materials, and figured out that they were actually bounded by what we'd already analyzed. So now we have an array of container materials that are acceptable in the facility. Finally, and the more extensive one is a few examples from my primary facility, which is the H Canyon. As the intro said, this is the nation's only remaining industrial scale radiochemical separations facility. So very complex process, but something that lends itself to a variety of improvements and enhancements. So the first one we're going to talk about is my personal favorite, the separations process. Separating uranium and plutonium from irradiated fuels and recovering the valuable materials is something that's been done for decades. But sometimes the analysis that go into that, especially for criticality safety, are very, very restrictive. So this was a mixer settler solvent extraction type process that used a aqueous feed nitric acid solution and a solvent, an organic solvent feed that includes tributyl phosphate and essentially a high purity kerosene as the diluent. Well, the old method says if I screw up my chemistry in any way whatsoever, all of my fissile material is going to be stuck in 3 stages in the mixer settler. 2/3 of it's going to accumulate in the stage where I messed up the chemistry, and there's going to be about 1/6 of it in the stage on either side of that. Therefore, given enough time, I'm going to have a critical configuration. Well, that's very easy to defend, but the problem with that is it doesn't obey chemistry. So solvent extraction chemistry, if you look at just the steady state version of it, you can balance, it's a balancing act, it's a mass transfer. So if we say that the Y values are concentrations of some material in the organic phase, and the X values, pardon me, are the concentration in the aqueous phase or the nitric acid phase, then they're related by this simple mass transfer equation where these capital E, S, and F are the flows of the solvent, the extractant, and the feed. They're related by what we call the distribution coefficient, this D value. That's the real hush-hush value, the chemical value that says how much of material A goes from the aqueous to the organic phase in this particular condition. And then because it's countercurrent, we can simply relate stage to stage to stage by what's going out of one is what's coming into the other. So in steady state, this is a very simple tridiagonal matrix algebraic solution. It gets a little more complicated when you introduce time dependence, but basically you just integrate over the volume of your system and how that's changing with time. The CFIS program does the actual dynamic chemical simulation of this process for us. So a few of us stepped back and said, okay, we have something that can actually model the dynamics of the chemistry. We have something that can model the neutron multiplication. Why have we not let these two codes talk to each other? So we ran simulations of the upsets in CFIS. We pulled stage and phase-wise compositions for each stage of the mixer-settler bank and put it into scale, calculated a neutron multiplication factor for it. Well, lo and behold, those upsets that we would consider that we're running to criticality no matter what, yeah, they get you to an undesired state. You may be losing product, you may have a higher inventory in your system than you anticipated, but it's probably not going to go critical. And to show that it's not going to go critical, we take the worst conditions. So for example, what you're seeing here is one of these acid dilution upsets where you have your aqueous phase uranium is what's shown here. These are 2 banks in a process for purifying the uranium. You can see that under normal conditions, which is the dark green line, fairly well managed. Under our credible abnormal conditions, which are the dark red and dark blue lines, you do have a perturbation. Yeah, you are changing how much materials in your system and where it's distributed. But honestly, it's not very severe. If we take this even beyond credible abnormal to even beyond the physical capabilities of the chemistry system, the mechanical design of the system, well, you can get to a point of concern, but at that point you have to ask, okay, I have a high concentration of uranium, but it's only in a few places in the system. Is it actually going to be a critical configuration? That's where we turn to scale. We model the chemistry in scale, and lo and behold, we don't have a critical configuration under any achievable condition. Well, let's look at the orange lines. I know this is kind of a busy plot. The 2 solid orange lines are our actual credible abnormals. That's the range where the system operates. Beyond that is conjecture. This is how far can we actually go with the chemistry. Eventually, you run out of head tank space for cold chemicals. Eventually, you run out of processed chemicals to dilute or to concentrate. But over the entire range of what's considered credible, in some cases, even if we double the size of the system itself, it's still not going to go critical. So a lot of these chemistry upsets are just not credible. The chemistry of the situation will not allow you to get to that point. Another big mission for a facility is if we're going to separate and purify things, well, we've got to get them into aqueous solution first. So one of the big missions is dissolving of mainly aluminum-clad uranium-aluminum alloy or uranium oxide fuels. We process 2 types, essentially, the Hyphen Cores from Oak Ridge and a variety of research reactor fuels. The old way to take care of Hyphen, you dissolve it 1 core at a time. You make a bunch of assumptions that the entire mass of the core ends up in an optimally moderated, perfectly spaced cylinder within the dissolver. And that leads you to, I can only do this 1 at a time. I have to have a lot of neutron poisons. And it's going to be a very cautious approach. Easy to defend, but very cautious. For those research reactor fuels, we assumed a linear uranium density and that we put, therefore, a mass limit in each well that we could put the material into in the dissolver. And on top of that, we added a soluble neutron poison. We put gadolinium nitrate into the solution to make sure it doesn't go critical. Well, that's all great. It's easy to defend, but it slows us down really, really much, a lot. So let's look at Hyphen. Well, we did a very detailed simulation of a very detailed Hyphen core inside the dissolver, so we could get a really good picture of what was going on. Well, if you look at the chemistry, it takes 3.75 moles of acid per mole of aluminum and 4 moles of acid per mole of uranium to dissolve. There's a lot of aluminum in a Hyphen core and only a little bit of uranium. Well, the maximum amount of acid that we can load into the vessel can only dissolve about 5 cores. And if you dissolve that many, you're not going to get a critical configuration. We had SRNL do a chemistry study for us, come out, determine that there's only a maximum concentration that you can have in any spot in the system because it's a very turbulent process. And the conclusion was the chemistry shuts you down. Before you can reach a critical configuration, you stop dissolving, and you just have a piece of undissolved core sitting there in the dissolver, doing nothing. So now Hyphen cores can be processed 5 at a time without any additional criticality safety controls, other than it's a Hyphen core and you're dissolving it in nitric acid. For the MTR, well, that stands for material test reactor. It's a general term for research reactor fuels that we use. We realized that we're placing them into a controlled geometry. And there are these plugs that have been manufactured for this dissolver that block off either 5 or 4 of those wells and further restrict the spacing between the materials. What is the I in Magic Mirv? Interaction. We're limiting the way that these can interact. So one of our guys went in, done a very detailed analysis of the dissolver with the 2 different types of plugs installed, even went as far as to say, okay, maybe we'll have an undissolved lump of fuel that somehow collects in the bottom of the dissolver. Not very realistic, but still conservative. Lo and behold, if we take the highest reactivity fuel type that we can receive, we put it into this controlled geometry, there is no physical way for us to overmass any of these wells to result in a critical configuration. So the result is, with the 5 or the 6 well plugs, with 5 or 6 wells open, you don't need any restriction on the fuel type. There's no neutron poison needed, even though the facility asked us to go ahead and keep it as a control, good defense in depth. I can't blame them for that, but it's not really needed. And what it boiled down to is the only really actual criticality concern is letting this stuff set for weeks or months and over concentrate once you've dissolved it. There's no well criticality concern, just for the bulk solution now. We've also been able to enhance a number of our missions in the HKM facility through downgrade or upgrade. I'm going to talk about a few scenarios now, and the results that we got had no impact, no input from criticality safety or nuclear engineering. We had chemists helping us out, we had mechanical engineers helping us out, chemical engineers helping us out, and they pretty much said, these scenarios you guys have thought up are completely impossible. They're bounding, easy to defend, but they're not possible. The facilities in South Carolina, this is one of my favorites. There was a theory that we could freeze these giant tanks of uranium solution. And despite the chemistry that happens, the uranium would somehow magically collect only in the solution, not the ice. Well, some of our folks went back, looked at the climate in Aiken, South Carolina between 1961 and 2017. Looked at the size of these tanks, anywhere from 5,500 to 163,000 gallons. And the result was, there is no way that in the climate we have, you have enough freezing weather to even begin to concentrate these massive tanks of uranyl nitrate solution. And by the way, uranyl nitrate freezes a few degrees lower than water freezes, so that's even another impact. But basically, chemical engineers were able to say, this is ludicrous, why are you even doing this? And the result is, we don't need to incorporate heating programs in some of these tanks to maintain minimum temperatures during the winter. Another one, outside facilities, there are sumps under fissile material transfer lines. The idea, or the postulated scenario was, okay, you can have a small leak that you don't detect and have enough fissile material build up over time to be a concern. Well, one of our chemists went in, looked at the solutions that could be there, which are uranyl nitrate and nitric acid, And we looked again at that weather from 61 to 2017. Only 2 months had no rain. The average annual rain, the minimum annual rainfall is 28 inches. The maximum leak that we can't credibly detect would take about 4 months to get just to the minimum critical mass. So it doesn't not rain enough in South Carolina for this material to not be redissolved and be moved forward to another piece of equipment that is mass controlled. So this event was determined to be not credible because of simply the basic chemistry of the solution and the climatology. The benefit of this is it also now prevents our operators in outside facilities from having to handle high concentrate acid by hand. So big OSHA improvement there. A couple of my chemical engineers actually came up with this one. The separations process uses 7.5 volume percent tributyl phosphate in an organic diluent. One of the postulated scenarios was that you could concentrate or dilute that material enough to where you're increasing the relative amount of uranium or fissile material in the process. So we gave them the limits where we thought this would happen. The chemical engineers went up and looked at this tank. This is one of the head tanks that pump in the TBP. You can't really tell it from the size there, but it's slightly bigger than your average trash can. The normal process will fill this head tank at most twice per operation. To get to the points where we said criticality might be a concern, you would have to fill this thing at the solubility limits, breaking all of your controls on sampling between 8 and 16 times per run to actually get to that point. It's just not credible that would happen. So those events are no longer with us. Finally, one of the things I'd like to talk about is how we've been able to do some mission enhancement by some simple upgrades. The Canyon has been tasked to bring back online its electrolytic dissolver to process some stainless steel clad plutonium. Well, this was typically used for uranium processing back in the 70s and 80s, but now we're going to be putting plutonium in it. So instead of just assuming 100% plutonium-239, which is bounding and simple and easy to defend, we used actual bounding isotopics for what's going in there. Plutonium-240 is a poison, so we let it be. We credit the design of the basket, which has some minimum spacing between the materials that are about to be charged. And by doing some very detailed analysis, we were able to say, okay, you can load any 2 of these at a time. You don't need to repack them, which saves worker dose. And all you need is that spacing and a little bit of neutron poison, a little bit of gadolinium dissolved in the system. The main feature there is that they can do these 2 at a time without repack. That essentially doubles the throughput and it saves workers from having to handle highly radioactive materials. And basically, it can even be modeled as a very simple system. Finally, it's always good to have something in your back pocket as an engineer. Even the things that we've talked about have some conservatism built into them, but just for the sake of it, we have created very highly detailed models of the entire facility, from the 70, 80 foot tall canyon structure all the way down to the individual fuel plates of the individual fuel elements in the dissolvers. These explicit geometries tell us that you can actually save an extra 0.1 delta K off of the values you're getting out of the current analyses. Unfortunately, each model takes a few days to run, so if you're running hundreds for an analysis, that's not quite practical. But if they're ever needed, they're there in your back pocket, kind of as a reserve. So I've said all that to come to the conclusion. What is a realistic evaluation? Finally, NSA 1 tells us to do process analysis, and that is the first thing you need to do, is thoroughly understand your process. I highlight your because you have to take ownership of this. You as a criticality safety engineer are actually doing something that is protecting a worker directly. The other thing is you analyze the normal operation of the process and what is a credible abnormal. Don't waste time. Don't introduce arduous controls for things that can't physically happen. This is a multidisciplinary approach. The operators, for one, know more about this process than you as the engineer are going to know. They know more about the process than the chemist is going to know, because they're the ones that are out there manipulating the equipment, messing with the material day in, day out, year after year, while we do a few analyses, document it, bless it off, and say, go do your job. Also, we should not be siloed as engineers. There are other engineering disciplines out there. There are also the chemists, there are laboratory experts, there are management. They know things too. Nuclear engineers are not the only engineers that know how to do their job. So get with those other disciplines, get their input on what is a realistic scenario and what you should actually be analyzing. When it's appropriate, introduce multi-physics. A lot of criticality safety is built around neutron transport calculations. But we can do other things than criticality simulations in scale and MCMP, including things like chemical interactions, actual mechanical designs of your systems, external conditions, fire protection conditions, the chemical engineering designs of the system. The actual thing is that the other parts of the design process affect what you need to be analyzing. Finally, validate and set a reasonable upper limit. Validation is a big computer word that has a variety of meanings depending upon who you're talking to. For us in crit safety, this means that whatever methodology we've chosen to use, be it a computer calculation, a hand calculation, a handbook value, that it is applicable to the system at hand, and that is proven out by comparison to benchmark experiments. And from there, we want to set a safe multiplication factor. If we're saying I'm going to protect a K equal to 0.964, I better have a darn good reason as to why I'm protecting 0.964 instead of 0.95 or 0.98 or whatever other term we might use. So that includes things like bias and uncertainty, subcritical margin, area of applicability, administrative margins. If I'm protecting this value and I'm confident that the system is going to stay below that multiplication, I better be able to defend why. Lastly, this is not all my work. This, as you can see, is a number of different people that have contributed over a variety of facilities. The criticality safety staff that have done these calculations and analysis, and then also our facility engineering and our laboratory staff that have contributed to them. As appropriate, I've thrown in a bunch of references that are way too lengthy to read off, but that is essentially all I have. At this point, we'll take some questions.
Thank you very much for excellent talk. What I ask is that if anyone has any questions at this time, please raise your hand. I'll call on you, and you'll be able to unmute your microphone. Or just go ahead and unmute your microphone and ask a question.
Yeah, so I got a question.
Okay.
My experience with crit safety is that whenever you take credit for realism, you're required to, by default, turn that realistic feature into a safety significant control, which is what typically drives people to go to these arbitrarily unrealistic, almost physically impossible scenarios because they don't want to have any safety significant controls. You have to go and monitor the thickness of a drum or the radius of a drum or things that are just arduous. It seems like some of what you did was identifying passive controls, but others, it looked like you actually were just trying to go with realism, but it didn't look like you were being also forced, or you didn't mention whether you're being forced to call out new safety significant controls in order to credit those parameters.
So yeah, you're right. It is a variety of ways that those play in terms of, I guess you call it functional classification. In some cases, we were able to credit the design of a facility, say a thickness of a wall, or the maximum flow rate of a design of an installed piece of equipment, or the thickness of a container. In some cases, we're able to credit natural processes. For example, the density of materials that could come into the MPF, or the climate that we actually experience in South Carolina. I know it may not be your most typical thing to defend processes like that, but those are not things that you really have control over. I mean, densities are what they are. Climate is what it is. In some cases, we did credit things like the chemistry of the situation. The Hyphen Core is a really good example. You can only get nitric acid to such a concentration while it's still in solution. You can only physically load so much into this vessel, and this vessel's already been designed and installed. It has a fixed capacity. So we did look for things like, what is the installed equipment that's already there? As you know, if you go to mess around with anything in a nuclear facility, it's a big process to change a design. So if it's installed, that's probably the design you're going to have to work with. I didn't really touch on it, but a lot of these times when we do these detailed design analysis, we are working from the as-built verified drawings of the equipment. I don't know if that completely answered everything, but it's kind of a broad question.
Okay, we have another question from on the chat board.
Okay.
From Mustafa Hamza asking, is assessing the credibility of a scenario decided only based on expert judgments, or was a probabilistic analysis employed and the probabilities of these scenarios decided this credibility?
I'd use the response, it depends, but it kind of does depend a little bit on the scenario. For some of the situations, it's a purely expert opinion because, you know, we have a physical design. The head tank one was a good example. You would have to load those head tanks a number of times, more than you would do for for actual running the process. So you can judge just based upon how the process is to be run and the design of those pieces of equipment that scenario is not credible. For things like the climatology, those were actual statistical analysis. You looked at, you know, what is the probability of having a month with no rainfall? What is the probability of having a month with only an inch of rainfall? Or what is the probability of having more than 5 days below freezing temperatures? And determined if those were statistically credible. So it really depended upon which one you were looking at as to the answer to that question. So I guess in short, both.
Here we have another.
That was just a thanks.
All right. Any other questions from the audience? Either unmute your microphone or please feel free to post on the chat room. All right. Going once. Going twice. And you are off the hook, Tracy.
All right.
So thank you very much for your
Thank you.
also excellent presentation, and thank you everyone else for attending. We look forward to seeing you look forward to seeing you all for next week's seminar on Thursday at 4 p.m. So thank you very much, and everyone have a safe week.
Thank you.